So this was well, supported by Simons Foundation and also by Decision Research Corporation. They supported some graduate students working on this. Saros Niraula here at University of Hawaii. Also Suwan Yoon, who is now actually in Chengdu, China. Okay, so what this paper is about is a certain family of distance measures for a given set. So if you have a given set and then certain subsets of it, then you can say what's the distance between A and B, and how should we define that? So the way this connects to the published literature is that there was a family of such distance measures defined by Jimenez, Becerra, and Gelbu, and we characterize exactly for which of the parameters, so the parameters alpha and beta, this ends up being a metric. And this family is interesting because, so for one choice of parameters, so half and 2, then we get the Jaccard distance, which is a famous distance measure. And for another choice, 0 and 1, we get something analogous to a distance measure that's been studied in information theory and computability theory, called the normalized information distance. Okay, so the history here is that there was one sort of Komogorov complexity based measure that was introduced in 2001 in a bioinformatics journal. And then some of these computability theorists proposed a modification, and it looks like this. And here, so by the way, the Komogorov complexity, what this means is like basically the shortest program for a computer, and so sort of informally speaking, shortest program printing X. That's the Komogorov complexity of X. And if it's given Y, that means that Y is like a database that's available to the program. So if X and Y are very similar, or if you can easily describe what X is in terms of Y, then this complexity of X given Y would be small. Okay, so here the distance between the two strings X and Y. So when would that be big? Well, if it's hard to describe X given Y, or the other way around, relative to how hard it is to describe the words by themselves. Okay, so this is an area of science where the different scientific fields come together. So this started in a way with this bioinformatics paper. Then there was a follow-up in the malware detection literature that was actually proposing kind of going back. So going back to the 2001 approach, not the 2004 approach. Okay, but let's get into what we're actually talking about. So here we have the Jaccard distance. So let's say we call it D of X and Y. And so what it is you take, let's say you have X and Y here. And then let's say we have some elements that are in both X and Y, or some are in X but not in Y. So then what we do is we take the cardinality of the symmetric difference and divide it by the cardinality of the union. All right, so in this example, can anyone see what the distance is? Yeah, so let's see, the symmetric difference, that would be those 5 things that are in one or the other, but not both. And then there is 7 in total, so 5 over 7. So that is the one measure of distance between X and Y. And then we could also have this more normalized information distance inspired distance here. So if we call this d hat of XY. Okay, so then in our example, that would be 3 divided by 5. Right, because we have the biggest of X minus Y and Y minus X is Y minus X, which has 3 elements. And the biggest cardinality of X and Y is the cardinality of Y, which is 5. Okay. So both of these definitions give us a nice metric on these sets, but now one could wonder, like, is one of them better than the other? And maybe are there other alternatives that are better than both of them? This has also actually been studied in a very different context, where instead of cardinality of sets, you look at random variables, and then you look at, so H is the entropy, and I is the mutual information. But other than that, it's the same formal pattern that's being used. Okay, so to state the main result a little bit precisely here, so let us define what's called a semi-metric. So now many people know what a metric is. And a semi-metric is just a metric, except that we don't require the triangle inequality to be true. So it's just a non-negative function. It's only 0 when the 2 inputs are the same, and it's symmetric. Okay, and then the definition that was made by Jimenez et al. Goes like this. So in terms of parameters alpha and beta, we define this fraction. So they were looking at it from the opposite point of view, where instead of distance, you talk about similarity. Okay, but so if we want to get a distance or dissimilarity, we can just do 1 minus that. Now there is one small issue when you have these fractions, is that you could end up dividing by 0. And actually, if you look at this, you see you'll actually only be dividing by 0 if X and Y are both empty. Well, unless so alpha and beta are 0. But that's okay, because we want to say that the distance between the empty set and the empty set is 0, so that's not the worry, really. Yeah, and in fact, we can make a little lemma here. So if you have a metric that works on all the non-empty sets, then we can extend it to also include the empty set in this way. So we just say that the distance to the empty set is 1 for every non-empty set. And this works as long as the original metric was bounded. We're actually interested in the case where the original metric is bounded by 1, but the proof only requires it's bounded by 2. Okay, now there are other metrics of similarity measures like this that have been introduced in science. So here are just 2 more examples. So just to illustrate that this is all over science. So one is the Simkivitch Simpson coefficient. So again, it's a fraction and involves the cardinalities of these different pieces of the Venn diagram. This is not a metric. Then the Kjos-Hanssen dice coefficient, another version or variation. Okay, so now let's see if we can state our results. So since we're talking about the minimum or maximum of the cardinalities of these 2 parts of the Venn diagram, so like this and this, let's call those little m and big M. So where big M is bigger than little m. So then in terms of that, the definition by Jimenez et al. Goes like this. So this depends on some parameters alpha and beta. It also depends on a bias that they were interested in, but in our paper, we're letting the bias be 0, so that goes away. And we take 1 minus that, and then we get this here, a little bit complicated formula for our potentially metric function. So the question is, for which alpha and beta is this actually a metric? So it's sort of a pretty elementary question to state, which is why it was amenable to being formalized in the proof assistant without too much trouble. So the result is that, well, we only really make these definitions for alpha between 0 and 1 and positive beta, and then here's the characterization. So alpha must be between 0.5, beta must be above 1/1 minus alpha. And what that amounts to saying is, in part, it's saying that we need to give higher weight on this max here than on the min. Okay, and here we actually have a picture that shows this result in context. So the result is that we actually have a metric when we're in this green area. So every point in this green area is a metric, it represents a metric. And anything outside here is not a metric. So in particular, this the Kjos-Hanssen dice and Simkivitch Simpson, they are out here in the not a metric area. I mean, it was already known that those are not metric, but now we see it sort of in a big picture. So what do we have to formalize to get this proof to be formalized in lean? Some little things, like for example, this lemma here, pretty easy lemma. And here's an extension of that. So if we have a metric D and it's given as a fraction like this, then it will remain a metric if we add epsilon times the numerator in the denominator. So that was useful in the proof. And then one of the interesting things that was found along the way is that if we just look at this sort of this numerator here, where we just have the minimum of these two parts of the Venn diagram and the maximum, and we take some sort of convex combination of them, then we can characterize when that is something that satisfies the triangle inequality. So it is whenever we put more weight on the larger of the two. So like this is the larger one. And the interesting thing is I first had a little bit messy proof of this, but then when I sat down to formalize it in Lean, if you try to formalize a messy proof, it becomes very painful. So I was sort of forced to come up with a nicer proof. And in the process, it actually discovered this identity, which I guess is trivial, but I hadn't seen it before. So this says that. So let's consider. Let's write x sub y to mean the cardinality of the set capital X minus the set capital Y. Then these numbers satisfy this sort of rotational equality here. So if you look at the things that are in X and not in Y, and the things that are in Y and not in Z, and the things that are in Z not in X. And so the picture will be something like this. So X and not in Y would be like this, and then Y not in Z would be this, and Z not in X would be this. Yeah, so you see we're counting everything that's in the union, but not in the intersection of all three. We're counting that once, and the same thing is happening on both sides of the equation. And this paper was apparently one of the first papers that are of the nature where you have a new result and it is published together with its formalization. So that's the claim to fame for this paper. And there are some other papers here that are formalized using Lean, but a lot of them are referring to old results, but like Hall's marriage theorem, but it's actually also a new result. But it's partly the reason that was possible was because the proof isn't that hard. Okay, so some open questions. So in computability theory, here's an open question. So remember K of X is this Komogorov complexity. And that's defined in terms of Turing machines and computability. Okay, so then we can make a function like this. So we take basically what we already did, but replacing the cardinality of y minus x by the Komogorov complexity of y given x. Okay, and we get a function that, so it takes strings and then gives a certain distance between the strings. And the question is whether that can be lower or upper semi-computable. And semi-computable means like not necessarily computable, but it's like it's like an increasing, I guess a bit lower semi-computable. It's an increasing limit of computable functions. And this is sort of interesting because K of X itself is actually upper semi-computable. So essentially, because to find the shortest description of a word, you can just start running lots of programs and you'll find some descriptions. And then you can keep track of what's the shortest description or the shortest program you found so far. Okay, so this involves something that's upper semi-computable. On the other hand, we have things both in numerator and denominator, so that could be a problem because if we can approximate something from above, then 1 divided by that we would only approximate from below, right? So like 1 1 over kx would be lower semi-computable. And then if you make a fraction of them, it probably is neither. And in fact, that was shown by Tversky and some co-authors that the answer is no, it's neither lower nor upper semi-computable in the case where alpha is 0 and beta is 1, which is this normalized information distance. So this question is just then, well, could there be some values of alpha and beta where the answer is yes? A conjecture would be that there can't be, but it's a little interesting. You know, what if we make alpha and beta be themselves non-computable numbers, for instance? There's also an entropy version of the main result that isn't in the paper, so I won't say too much about. But yeah, we guess so. Basically, the same type of result, but now in terms of conditional entropy and mutual information. Okay, and then so here's a nice problem that's left open that might be reasonable for students to look at. I'm not sure. So let's look at this in a different way. So instead of connecting the Jaccard distance to this analog of the normalized information distance in the way that Jimenez and the co-author did, let's look at it in a different way. So when you see the maximum like that, then you know maybe it's natural to think of this as sort of like an L infinity norm. And when you just have the cardinality, yeah, maybe that's more like an L1 norm. And actually, yes, that is possible. So yeah, it took me a while to see how one can do this, but we can do it like this. So you can define. So now remember, J1 is the Jaccard. And J infinity is this other one, normalized information distance. But for any t, you can define this strange sort of algebraic expression here. So it's all a function of the same cardinalities of the different parts of the Venn diagram, but we're raising it to the p power in certain places and taking a little bit maybe unmotivated looking fraction there and taking the pth root. Okay, but that's all designed just to make this equality here be true. So that's the motivation, is that if you let p equal 1, then indeed it is the Jaccard distance. And if you let p go to infinity, then you can see that it goes to this normalized information distance. So the open question is this JP, is this actually a metric for every value of p? And this could be, would it be tedious to check? Probably. Would it be doable? Maybe. Okay, so that's all. So thank you very much for listening.